Very good. Professor Lawler did his PhD also in Princeton under the supervision of Ed Nelson. He held positions at Duke and Cornell before going to the University of Chicago. He is a member of the National Academy of Science. He was an invited lecturer at the ICM in Beijing in 2002, was a plenary lecturer at the ICM in Rio in 2018. And amongst his many awards included the 2006 Siam George Polya Prize with collaborators Oded Schramm and Wendelin Werner, and the 2019 Wolf Prize in Mathematics. I met Greg in Vancouver at PIM's conference on financial crisis, and we bonded over beers at the UBC student bar, and I think over a common suspicious of mainstream economists, but I don't want to put words in his mouth, and I'll let him go on with his talk.
Okay, thank you for the nice introduction. And I'd also like to thank the opportunity to speak at this conference, where it's a chance not just to talk about mathematics, specific mathematics, but also about the industry of mathematics, or the field of, the role of international mathematics, how is mathematics done, and a little bit of the role of metals. But so I'm going to try to add a little bit of that into my talk. So a large fraction of the work in probability in the last 30 years has been motivated some way or other from the physics community, and a subclass of that comes from what's called critical phenomenon in statistical physics. Just little ideas here very quickly. We have measures like configurations that depend on a parameter. So this parameter is one over temperature. So, and for these sort of phase transitions, when you have low temperature, it looks some way. When you have high temperature, it looks some way. And there's a sharp transition. Well, I'm not going to be doing any physics here, but I will just say that most of what I'm talking about is discussing what happens at that sharp transition point, the critical phenomenon, what's happening at the critical phase. So actually, I think maybe I'll skip this slide, or I'll get to this later. I'll go to slide quickly. We'll just, I'm going to talk about the self-boarding walk. So this goes all the way back to Paul Flory, a chemist who eventually received the Nobel Prize in chemistry for work related. Well, this may be considered part of a large amount of work he was awarded for. But the basic, simplest idea is you have a polymer dilute solution, and it looks random, except it interacts with itself in a way so you can't hit yourself. So that leads to the natural elementary way of thinking about this. Let's look at just lattice paths that have no self-intersection. And let's understand that first, and then we'll get on to the hard problem. Well, I will tell you the state of art now is we've done a lot of that hard problem, but we still don't understand this little simple problem that we started with. It turns out the simple problem is harder than everything else. And so if you say, I'm not quite sure how this works. Oh, maybe I should do that. Yeah, okay. So, but let's just talk about the self-boarding walk as a mathematical problem. There's a picture I was just giving Tom Kennedy, Arizona, who's one of the gurus for simulation of self-avoiding walks. I'm not such a guru. So, but I also want to give another picture, which comes from the early 80s. And this is from Benoit Mandelbrot's book, The Fractal Geometry of Nature. Now, the picture quality is not so good here. So what you don't see here is how this blob was formed. I'll just say what he did was take a random walk, just a regular random walk, condition it so you start and end at the same point. So there's a random walk in here. And now a lot of these places on the inside the random walker did not visit, but this sort of outline, this boundary is the outer reaches of where the random walk visited. What's called the outer boundary. And he looked at that, and he was aware of Florey's look at the self-avoiding walk. So he knew about that, and he knew that Florey had, I'll go, okay. That Florey had actually predicted what the dimension of this was, and Mandelbrot said, that looks like self-avoiding walk. Now, I'd like to just say a little comment. I mean, there was talk earlier about conjecture versus theorem. How is mathematics derived? Well, in my area, the physics community is a source of many of the most exciting problems that we see. There's also, Benoit Mandelbrot is sort of an outlier in all of this. He's a mathematically trained person, but he didn't do, to be honest, didn't do that much in mathematics if we measure mathematics in proving theorems. But he did amazing things in mathematics in two areas. One, in finding things that we hadn't seen, just to look at that. And also in the area of making difficult mathematical ideas accessible to people in other areas. And I think some people don't appreciate that achievement's enough. In fact, he got the Wolf Prize in physics, even though he actually wasn't a physicist as far as I could tell, because of his ability to introduce fractals to physics. But I'm going to look at that outer boundary there. Okay, let's return to the self-avoiding walk. I'm just going to give you, so if I let Cn be the number of self-avoiding walks starting at the origin, there's a little exercise that it's sub-multiplicative. If I take a Cn and you just do this, and you can see that the number of self-avoiding walks grows like a power law in a weak sense. This number is not known exactly for the square lattice. It is on the hexagonal lattice, and just because we're supposed to put up Fields medalists here, the ones who actually did that are Stas Smirnov and Hugo Duminel-Copan. I will say both of them have more on their Fields resume than just this result. But if you look at, you actually want to say, how many self-avoiding walks are there? Well, if you want a self-avoiding walk of length 2n, the very simple thing is you take a walk of length n and you put another walk of length n and you put them together. And then that may or may not be self-avoiding. And you do ask the question, what's the probability that it's not? Probably that it is self-avoiding. Probably it is self-avoiding. And you get a phenomenon that you see in statistical physics a lot. What happens? Well, one dimension is trivial. I don't even talk about one dimension. In high dimensions, there's so much room that it doesn't want to hit itself. So you can, and that's actually a theorem. I will say it's, what you say, it's sort of some trivial behavior in high dimensions, though it's not trivial to prove it. In a critical dimension, d equals 4, there's a logarithmic correction, and then there are exponents in the smaller dimensions that are often called critical exponents. And this 11/32, you actually, if you're at Stas Smirnov's talk, you heard that was the 11/32 that he talked about, that Nienhuis was the first one to predict. And then for d equals 3, for a lot of these models, the exponents are expected to exist, but there's no reason they take on any nice value. So here's predictions. Now, let me talk about the word prediction. We were talking about conjectures and theorems. Well, in the areas that I am dealing with theoretical physicists, the word conjecture to physicists is way too weak a word. Conjectures for them are like wild guesses. And a lot of work in the physics community, while far from rigorous, maybe not even being rigorizable, does have theoretical content to it. And at least my group of people, we compromised on the word predictions. So when the word prediction is used, it's not rigorous, but it's acknowledging that there's a fair amount of serious thought behind it. Okay, so Flory predicted a certain thing for the self-voiding walk. I'll actually say to give Flory the word prediction is a little kind to him. He didn't have all that much argument. But it turned out to be a particularly good argument. He said that the typical length of a self-voiding walk of length n would be n to the nu. If it was a random walk, basic random walk, it would be 1/2. This is a basic fact about all probability. If you do n something n times, the error is of order root n. So 1/2 would be if it's completely random, but for smaller dimensions, it gets bigger. And you see here, Flory predicted nu equals 3/4 for d equals 2, which turns out he seemed like he was right. D equals 3, he gives a nice number 3/5. Nature tells us 3 dimensions doesn't have nice numbers. The actual number seems to be about 0.588 ... but it's not too far off. And his methods were not good enough to determine the logarithmic correction in 4 dimensions. I will say that the scaling limits were supposed to be Brownian motion for d greater than or equal to 4. That's been proved by Heron and Slay in more than 5 dimensions. It's not a trivial result, but it is a perturbation from Brownian motion. You expect to be Brownian motion, you try to show it. That's also true in 4 dimensions. That's still open. We now know what we would expect it to be in 2 dimensions. I will discuss that here. And it's unknown for d equals 3. And if we talk about dimension, I'll tend to say fractal dimension rather than Hausdorff dimension, only because there are a couple of different notions of fractal dimension, Hausdorff, box, and things like that. And especially if I'm making heuristic arguments, I don't want to be too precise. It's just 1 over that, because anything is in terms of dimension. Okay, so that's this simple problem we had. That's actually not how it really arises in models as equilibrium statistical physics. Now, once you think of my talk here as being somewhat complementary to what Stas Smirnov did. Stas Smirnov was looking at examples, looking at the entire field, and inside those fields, you get sort of curves. I'm a random walker by heart. I'm focusing on sort of the curves that would exist in this. So I'm just looking, so here's a model just for self-avoiding walk. I'll take a big lattice. So there I have an n by n square, which we can think of as a 1 by 1 square with lattice spacing 1 over n, just always think. And now we just look at all paths from 2 boundary points that are self-avoiding. And it turns out we don't actually want to give them all the same measure. The natural thing to do is give it measure proportional to the length. They're actually e minus beta times the number of steps. There's a certain amount of energy for each step. So that's still just as elementary a problem, n by n thing, and there's only a finite number of walks, and each has a certain measure, so it's elementary. But you want to know what happens as n goes to infinity. So we first ask for the word partition function, it just tends to be used the total mass of a measure. So that's just the total mass there. And then the criticality comes in that there's a critical value of beta, so that as n goes to infinity, this neither grows exponentially or decays exponentially. It grows like a power law, or at most a power law. And the prediction is, in fact, that as n goes to infinity, that really should be an asymptotic there. Zn should look like n to minus some exponent. That's actually another critical exponent. And then times a factor here, which is something which will be something that exists in the continuum. Something in the continuum limit, we'll be looking at, say, a square of side length 1 with 2 boundary points. And then the typical path here, we would just be of order n to the alpha steps, where alpha is the fractal dimension. And then the Flory prediction would be alpha equals 4/3. So that b equals 5/8 is also, well, we're going to see that turns out to be something that's, we don't know rigorously, but we can try to get to this. So we're trying to understand what something like this looks like. What do we do? Well, we want to take the limit as n goes to infinity. And the right thing to think about is to say, okay, I'm going to try to assume there is a limit. What would it look like? So let's be a little more precise. We have in this situation, we have a path. The typical path has n to the alpha steps in it. So what I'm going to do is I will scale time so that takes time 1 over n to the alpha to go through a little path, to go through one step. And they'll do n to the minus 1. This is now a measure on continuous curves. And now the lattice paths are now, think of linearly interpolated curves. It's like that. So now that's still an elementary thing. We'll multiply this by this n to the 2 beta so that we get something of order 1. And then we expect to have some kind of continuous measure on paths. This measure actually will have total mass given by this number here. Sometimes we want to make it into a probability measure. So we'll just scale to a probability measure. Okay, that's the kind of thing that we're thinking about. Now here is where the physics community was very helpful to the mathematical community. There's Polyakov and many others who got to the idea that scaling limits of these critical systems should exhibit conformal invariance. Now, for those of us who are not physics oriented and fairly feeble-minded, we didn't quite understand what they said, but we've made rigorous ways of saying that. So in this case, for this model that I said, there's an easy way to talk about this. I did a square, but instead of a square, I could have approximated by some other set like that. And so I could take a limit here, which would be a limit on paths. By the way, this is a bad picture in the sense that these are actually fractal paths, but they're hard. Fractal paths are hard to draw, but we have a measure on paths. And then if I take a conformal transformation of the domain, we get another measure here. And basically the assumption is that if I take the lattice limit here and then map over here, or if I take the lattice limit directly here, we get the same thing. Or at least the same thing for the probability measure. The total mass also has a correction. So it's just the terminology we use when we have a correction, we say covariant. When we just have it completely equal, we say invariant. But there's another property that these have, and that's called a domain Markov property. And think about from the self-avoiding walk. Suppose I'm doing a self-avoiding walk from Z to W in a domain. And suppose somebody's told me the beginning and ask, what does the remainder look like? Well, the remainder looks like a self-avoiding walk in the domain, except that I'm not allowed to hit what I've already seen. In other words, it's a self-avoiding walk in the slit domain. So those are two ideas, and I would say I sort of knew that in the 90s, but very important thing. I'm going to put one picture up here, and just because we're talking about the Fields medal. The Fields medal is something given to people who there's a very sharp time where you have to be in order to get the Fields medal. This is probably one person who lost the Fields medal for being 2.5 weeks too old. He actually had every reason to believe that he would have been a winner in 2002. This is Oded Shram, if he had not been born, if he'd been born 3 weeks later. But the Fields Committee or ICM, I don't know who the powers to be are. made a sharp rule on this. But he gets to be at the conference here. See this. Worst thing is that, I mean, he was a brilliant mind. Unfortunately, he died in a hiking accident in the mountains in 2008, I think. And so we have lost him. And I said, there's one person I'm putting up on the slides. If I put you up, then I have to have a lot of other pictures as well. Okay. But what he showed was that there was if you assume conformal invariance and the domain Markov property, there was only a one parameter family of possible limits. And that was a fundamental idea. And at that time, as just about the time he was doing that, I was doing work with a young probabilist at the time, Bendel and Werner, really trying to understand what's called the Brownian intersection exponent, which is a generalization of what you see at the boundary of the Mandelbrot. And we started working together. Bendel and Werner, definitely a Fields medalist, 2006. This isn't quite the order of things. I'll just say that our work shows that there is only one possibility that could be the scaling limit of self-avoiding walk. In other words, if the self-avoiding walk has a conformally invariant limit, as the physicists predict, then we know what it is. And at that continuum level, we can actually say that those numbers are correct. We also proved a strong version of Mandelbrot's conjecture, which is that this thing at the boundary of the Brownian motion actually is a version of this SLE process with 8/3. By the way, I do want to make the comment about Mandelbrot. There's a worry of mathematicians at times not getting credit for actually proving things. So someone would say, well, Mandelbrot showed this in 1982. Well, I can also point out some other parts of the book where Mandelbrot said things which are going to be absolutely wrong in the future. So let's give Mandelbrot the credit for producing the problem and showing us something good to look at. He didn't quite understand the whole subject. Let's just be honest. Okay. So I'm going to give you a quick definition of SLE just to see where two fields in this. So suppose I'm going to let my simply connected domain be the upper half plane and the 2 points be 0 and infinity. So I have some random process here. After I've done the random process for a while, what I'm going to do is I'll say, well, I'll look at the complement of that, and I'm back to complement back to the upper half plane. That's using Riemann mapping theorem, and you specify the conditions at infinity in a way to make it unique. You also reparameterize the curve in a nice way. And then it's a theorem from complex variables, Loeffner, that says that this map, GT, satisfies a certain equation. And there's this UT, which is just a real valued function. You have a real valued function, and you can go backwards. You can start with a real valued function and go that way. And then if you knew that fact, i.e. you knew complex variables, you would also know, you could also, if you knew enough probability, you would also say that, well, if it's conformally invariant and satisfies the domain Markov property, the only possibility for this UT had to be a Brownian motion. And that's basically what Oded observed in this fundamental paper in 2000, published 2000. And I won't go through this because I'll just say, so he said, when we're looking for all these things, there's only one parameter family. Now, I've changed history a little bit in the sense that self-avoiding walk wasn't the model that he was most interested, that he was concentrating at the time. He was concentrating on two models, mainly, one called a loop race walk and one called percolation. But before I do that, I'll just say that when you do these things, it's a very funny thing is that we've defined a path by not defining the path, but what we defined is the conformal transformation off the path. And now we actually have to describe a path by boundary behavior of conformal maps, basically. So that's the kind of stuff you need to do, but you find out you get fractal paths, depending on this one parameter kappa, you get different dimensions from kappa from 0 to 8. You get fractal, we proved the Hausdorff dimension 1 plus kappa over 8. And in fact, you can parameterize it by content. Now, this is one thing I do want to say. What's something that's sort of done a lot of the probability community now, not so much in other areas, is Minkowski content, for fractal Minkowski content. So if I've got an alpha dimensional set, and I want to talk about the alpha dimensional measure, one might say Hausdorff measure. But Hausdorff measure tends to be 0 for random sets, unless you have corrections. But this very simple thing of just fattening the set up a little bit by epsilon, take the area of that, normalize by what it is, and then take the limit. This is a kind of limit that tends not to exist for deterministic sets, but does exist with probability 1 for random sets. So Minkowski content actually is actually the main way to give the alpha dimensional measure on sets these days. Works very well for random sets. Okay, so what about the other parameters for SLE? Well, I'm just listing some here. Loop race walk, outer boundary. In all of these cases, all right, there's something particular about those problems that allow it to be solved. Schramm's theorem is not directly used at all from his original paper, but he gave the answer sort of like in the back of the book. He said it should be the Schramm-Lerner evolution, and then all of these things are proving that it goes to a Schramm-Lerner evolution in some sense. Now, I don't want to talk about these papers running out. I want to talk about two other conformally invariant things that are actually relevant to this, having something to do with current research. One is random walk loop measure. So this is actually a very elementary thing. I won't go through, I'll just say it. You can read as you go along. Just take simple random walk paths that are allowed to have intersections and give every path of length n measure, well, 4 to the minus n. That's just the probability of doing it. And then you put an extra 1 over n. And it just gives you a measure on things. And if you take your AN and put the paths more and more in there, you get more and more loops. And you actually get a interesting thing in the limit, something called Brownian loop measure. Something that Bendler and Werner and I discussed, looked at as an offshoot for some of our work with ODED. And it's like almost everything you do in mathematics, you find someone else had some of the ideas ahead of time. So there's work of Szymanczyk in the 60s that actually has some of the formulas we have. But the reason I want to bring it here is that at the discrete level, you end up seeing that the total measure of loops is minus log determinant of a discrete form of the Laplacian. So in the continuum, you actually have a determinant, or the log determinant of the Laplacian. Now, there are various ways people do the log determinant of the Laplacian without anything probabilistically. But actually, for those who have to deal with, take the Laplacian on a domain, looking at the determinant of the Laplacian, which by its nature is an infinite object, but you regularize it the actual Brownian loop measure in Brownian is actually a good way of doing this. And in the physics literature, it comes from weighting the polymer measure by this determinant to the minus C/2. So we have the same picture where we can take this path and we give sort of the same weight, either minus beta n, but now we have a factor here, which is the exponential of the measure of loops that hit this. And then there's this exponent, which I'm using the physics notation for. C is called central charge. And for C equals -2, this is what's called loop erase random walk. And that's for C equals 0, it's exactly what I gave for the simple random walk. And it's conjectured this would be same sort of conjectures are for this thing. Now, this is a kind of backwards conjecture in the sense that most of these conjectures were given for using the loop erase random walk, but also using SLE, looking at the continuum limit and looking at the continuum limit saying, let's go backwards and see what happens. So I just want to talk about loop erase random walk, and that's where there's been a stronger result I do want to talk a little bit about. All those results I talked about, convergence to SLE, use this new parameterization. When I talk about, if I have a curve, if I drew a picture on the board, I would say that's a curve. Now, when I have a curve, there are many ways to parameterize a curve. And there's actually 3 that come up in our thing. And they're singular with respect to each other. One is the capacity from the Loebner equation. And that's basically given by, if I take a piece of the curve and I'm far away, how much do I feel what's been added? Roughly speaking, thinking that way. The Minkowski content is actually the actual length of the curve, is a very local thing. It corresponds to the limit of the number of steps. There's a third one I'll give in a second. And I just want to say, with work with Frederick Wicklund and Christian Benish, we were actually able to show the scaling limit using the parameterization we had before. And it converges to SLE with the natural parameterization, with the, in this case, it's the 5/4 dimensional parameterization. Okay. Now, sort of quickly, there's another thing called a Gaussian free field. And this is getting a little bit to where we actually have a whole field here. So we had our square. Now we can try to put, so there's my square, my discrete square, and I can put a Gaussian random variable at each point. A mean 0 normal random variable. That equal is a typo. That should just be zx times zy. Expectation of zx times zy is that. And in the limit, as the square goes, you end up with a continuous Gaussian field, which is not quite a function. The variance at a particular point goes to infinity, but it doesn't take much smoothing to make it a field. It's sort of kind of like, I often think of it as being a signed measure that's not really a measure. It's finitely additive, but not countably additive. And in some sense, you think of it as a random harmonic function. And now you have pluses and minuses. How do you get something that's plus? You just take the exponential of it. You just take the exponential. Okay, there's a lot of technical work that has to be done to justify this. But there's a normalized exponential of this. And now this third way that of measuring the parameterization comes from this sort of, what I do is I will exponentiate, I'll take my curve, I have an independent field, and I will exponentiate the Gaussian field. So I'm really doing a random environment for those who like to talk about that. We're now talking about, and this arises in the physics descriptions where they're often not just integrating over points and curves, they're also integrating over geometries as well, metrics. And I will just say, if I choose the right value of this for a particular kappa, it happens to be square root kappa over 2, the natural parameterization is a alpha dimensional parameterization. It scales like that. If I want to have a one-dimensional parameterization, it should only live on about 1 over n points. So just plugging out that, and there's a particular value that does that, and it's sort of the quantum length ends up being a one-dimensional pattern. Turns out a lot of these things turn out to be easier in the random geometry. I'm just going to summarize a couple of things here. So a Gaussian field, so it was a random harmonic function. If a harmonic function u, value of u average on a curve, it has mean value property. Random harmonic function, expected value is the average value. If I have a harmonic function, I can take a harmonic conjugate. Smirnov mentions this as well. I mean, this is why the planar world is so beautiful. Harmonic functions we have in all dimensions. In the planar world, we have harmonic conjugates. So I can take a random holomorphic function. If I have a random holomorphic function, think of that as being, well, actually, let f be an antiderivative of that. Then we take the absolute of f prime, where it's an antiderivative of that. And the random metric is e to the h. In this case, h is the Gaussian free field. E to the h, if you heard these words, are either Gaussian multiplicative chaos or Liouville quantum gravity. Now, something I'm not at all going to mention today is the fact that this can be described as a limit of measures on discrete objects. There's a whole thing about random triangulations, random quadrangulations, and limits of that. A beautiful subject. And if you're interested in that, ask someone besides me. It's not my field. There's also another metric. Once I have a random metric, there's also something called the equivalent of first or last passage first percolation, which is if I have a very random singular thing, and I want to say, I want to get from this point to this point, I can say, well, let me find the best curve to do it. And that defines it. And there's a whole subject in there going on. Okay. So it's a very active field. I just want to, I want to discuss a different open problem. I'm not going to do it in much detail. Everything here has been two-dimensional, as was pointed out this morning. It's too much 2 dimensions. We want scaling limits in 3 dimensions for loop race random walk or SLE. Loop race walk or self-avoiding walk. I'm going to just give a very open question. Find a good measure on 3-dimensional paths that grows a path. I want it to grow a non-intersecting path, non-self-intersecting. I want it to be path Markovian in the sense that the distribution of the future only depends on where you've been before. Not Markovian, not just in your original point, but depends on the entire path. It should give paths of fractal dimension strictly bigger than 1. Find a way of doing it. Okay. I just do want to, what I said, a little started. I want to end with one comment about prizes, or not really about, one talks often about prizes in terms of the individuals who get them. But in terms of the Fields Medal, the Fields Medal had a very positive effect on probability as a field. So the fact that medals are given to people in a field, not just acknowledge the person, but start acknowledging the field. And probability has been surging through the 21st century. There are disadvantages of this. Now I find the number of very good young people keeps increasing, and I can't keep up with what they're doing. And it's the fault, but in other ways that, I mean, in 2018, the section for probability was probability and statistics at the ICM. So probability had half a section. The next time around, not only did probability have a full section, but in some sense, it was the largest section. There's a little cheating there because one of the reasons it was large is because there are a lot of people with joint sections. And that's key. Probabilities become part of so many other areas of mathematics. And this is something to celebrate. And that's what I would like to end with.